Hello guys, this is a screencast for simple harmonic motion. We will start with a definition of what is an oscillation. So an oscillation is the repetitive variation with time t of the displacement x of an object about the equilibrium position. Let's take some examples to understand more what oscillation means. In here we can see that we have a simple pendulum. We have a bob attached to a string, and it is undergoing a repetitive cycle of oscillation. That's another example. This is a mass on a spring, and as it's being displaced away from its equilibrium position, it will start to repeat the motion, the cycle, over and over and over again. That's the last example that we will look at. It's when we have a mass attached to two springs, it will start to repeat its motion over and over again. So we have so many other examples, such as the periodic orbit of the Earth around the Sun, of the Moon around the Earth. We have the hand of a clock, we have the cycle of a wheel of a car, and all the other amazing examples that you gave me. Over here, I'm going to take the example of the pendulum. This is the pendulum at its equilibrium position. We displace the pendulum and then we release it. It will start to oscillate, so it will go through its equilibrium position, back to the maximum displacement on the other side, and then back to the equilibrium position. This represents one full cycle. Now I'm going to try and take a screenshot of these positions. Okay, and this is the result. We will draw now the variation of the displacement of the simple pendulum in time. So we need our x-axis, which is time in seconds, and the y-axis, which is the displacement x in centimeter. We will have the maximum displacement and on both sides. Okay, so we will have the x0 and the minus x0. And okay, let's try to draw the variation. This is the equilibrium position. Oh, that's a bad color. Let's take red. So that's the equilibrium position. This is the point where we started the pendulum. The pendulum will reach the maximum displacement somewhere here, and then the pendulum will go through the equilibrium position again, and then we will have a maximum displacement, but this time on the other side, so somewhere approximately here, and then back to the equilibrium position. And so the variation will look something like this. This represents one full cycle. Okay, one full cycle. It's called the period t, denoted as t. That's in seconds. Over here, we're gonna prove that the oscillation, the periodic oscillation, will trace a sine wave. So if you take some sand and pour it in a container attached to a simple pendulum, and then you displace the pendulum with a specific position, and then you carefully start to pull the card below it in a periodic way, so in a periodic interval of time, you will see a beautiful sine wave that is being traced over it. Now we will see the variation of the velocity in time. So our axis would be v versus t. Now, it is important to know from topic 2 as a recall that we know the velocity is equals to the change in the displacement divided by the change in the time. So if you look at this graph, you will see that this relationship is given by the gradient. Okay, since we have a variation with x, you can then say that at each and every point of the graph, we will have a different velocity that we can trace over here. Okay, so take for instance the gradient at this point here. The gradient is the tangent for this point, and it shows a very high gradient. And as we go away, okay, as we trace it, you can see that the gradient gets smaller. Now the gradient at this point is equals to what? It's equals to 0. Gradient once again starts to increase, but in the negative sense. Okay, let me just take this. Yeah, gradient increases. Okay, that's the worst gradient. Gradient increases and becomes extremely steep at this point in the negative sense. Okay, so the gradient of this and that are the highest, the steepest, which should show what the maximum velocity. Okay, so I'm gonna use this marker. At this point, we will have the maximum v, and this will start to decrease gradually. So we will have a decrease from this point until this specific point where the gradient is 0. So our velocity would be 0. And then once again at this point, it will start to increase in the negative sense, so we'll trace it downward somewhere here, until this point where the velocity once again will be now maximum, but in the negative. Okay, now notice that this and that aren't quite symmetrical, but anyway, the shape will look something like this, okay, where this point will lie somewhere here. Alright, I tried my best and this is what we got. You can see that we have the critical points which show that at displacement 0 velocity is max, at displacement max velocity is 0, displacement 0 velocity max, displacement max velocity 0, displacement 0 velocity max. Alright, now what about the acceleration versus time? So we know that acceleration is equals to the change in the velocity divided by the change in the time. Axes A and T, by the way, this is supposed to be meter per second. I just changed it, just noticed. Yeah, back to acceleration. So acceleration would be the gradient of this line. So once again, I'm going to try and have the specific points in order to trace my acceleration. And you'll see that at this point, the gradient is equals to 0. And hence my acceleration, the gradient is going to show us a 0 point. So over here, we start from this point. Yeah. And then this acceleration, or this gradient, sorry, will start to increase until we reach at this point where the steepness of the gradient is the greatest. So we will have, but the gradient is negative, right? It's now minus, so we will have at this point somewhere here, the maximum acceleration in the negative sense. And once again, this gradient will start to decrease until we reach this point where the gradient is once again 0. So at this point exactly, we will have 0 acceleration. Now gradient will start to increase in the positive sense until we reach at this point where the gradient becomes positively, okay, whatever. So this is the point where the gradient becomes what? Max in the positive sense, so somewhere here. And then again, gradient is what? It's 0 at this point. Yeah, and trying to trace it now, trying my best, we will get something like this. Okay, this part isn't quite good. All right, look at this. Beautiful, isn't it? So what we can see is that these two graphs, they show us the same exact variation, but so they're proportional, but acceleration is negative whenever displacement is positive. So this can show us that acceleration A is proportional to x, the displacement, but in the negative sense. Yay, okay. Now let's draw this variation on a graph. So if we have our axis A versus x, okay, we know that these two quantities are proportional, but in the negative sense, which means that a proportional relationship is what is a straight line, right? In the negative sense, that means that your gradient should be negative. And so from this point, you will trace a negative line going downward all the way, somewhere like this. Now you should pay attention to something, that the variation here is minus x0, and here it's plus x0. So this shows what the oscillation, are they equal? 2, 2, 4, 2, 2, 4. Yes, they are. Okay. Now what does the gradient of this line give you? So what is the gradient of the line equals to? Gradient of the line is equals to omega squared. And where omega is what? Omega is the full cycle of the pendulum. So let's take this pendulum, for example. We know that if we start from this point, the oscillation represents, okay, I tried my best. This is what 2 pi, okay? So omega, the angular velocity, is equals to the displacement, which is 2 pi, of the pendulum, divided by the time, which is 1 full period t. And this is exactly what your gradient line will give you. It will give you the square of this omega relationship. And if you want to know why, you should know some math, which I'm going to show you. So I'm going to take these graphs, okay? I'm going to show you the derivation using mathematical equations. Okay, so this graph over here represents a what? Okay, so that's a sine wave, okay? And you should know that the quantity that multiplies the function represents the maximum of the y-axis. So here we have displacement, so this represents the maximum displacement. Sine is the shape of the wave, and omega represents what? Omega is, as we said, it's the 2 pi divided by the t. You don't really need to substitute it by that, you can just keep it as omega. Now in order to find v is the derivation of x in time. So if you want to derive this expression in time, you will get x0 omega, and the sine turns into a cosine omega t. And so v is equals to x0 omega, cosine omega t. Yeah, once again, this quantity over here represents the maximum of our graph, which is v versus t graph. So this is our maximum velocity. Last thing, if we would like to find the acceleration, we would derive the velocity in time. So the derivation is x0 omega of cos omega t in time, and you will get that acceleration is equals to x0 omega squared sine omega t and minus y. Well, these are the rules. The derivation of sine t in time is equals to cosine, and the derivation of cosine t in time is equals to minus sine. Okay, now once again, this is the quantity that multiplies my sine wave. So that represents the maximum quantity of what? Of A. And so we can have that x0 is the maximum displacement of the pendulum, v0 the maximum velocity, v0 has an expression equals to x0 omega, a0 is the maximum acceleration, a0 has the expression of minus omega squared x0. Okay, and so look at this. This represents what? Represents the gradient of our line. And it shows us also the relationship between a and x, and it shows us that they're proportional, and that the factor of proportionality is the gradient, which represents. In exams, you will be asked to state the two conditions for simple harmonic motion. So you'll say it's the motion that takes place when the acceleration is directly proportional to displacement, when there is a restoring force acting towards the equilibrium. In other words, in this pendulum right here, when you displace it away from the original position, the restoring force F is the reason why the pendulum will start to oscillate back and go back here to this position. And then once again, when it reaches the maximum displacement in the negative sense, it's the restoring force that will force it back to its equilibrium position. And this is purely because according to Newton's law, we know that F is equals to ma. And once again, we can see that A is proportional to the displacement, and hence F is also proportional to the displacement, but in the negative sense. All right, now let's look at the energy graphs for the pendulum. Now, the first thing that you should know is that energy cannot be negative. So our graph should not have a negative section at all, okay? Both graphs for potential energy and kinetic energy should only be positive. This is our EK, the kinetic energy, and this is our EP, the potential energy. Starting with the kinetic energy. So at this point over here, the kinetic energy should be maximum. Okay, note that the variation of the energies is with respect to displacement. Okay, so our x-axis is the displacement. Now, starting with the kinetic energy, we know that every time we're passing a maximum displacement, the kinetic energy would be 0 because we will have maximum potential. And every time we pass through back to equilibrium, this is the point where the system should have the maximum velocity in order to be able to oscillate to the other side. So at this point, the equilibrium, we will have maximum kinetic. Once again, maximum displacement will give us minimum or 0 kinetic. Equilibrium position will show us a point where we have a maximum velocity. And the graph would look something like, and the graph will look something like this. Yeah? Now, as for the potential energy, now every time we have maximum potential, we will have minimum kinetic, right? I said that right? One second. Every time we have maximum potential, we have minimum kinetic, yes. So at the maximum kinetic over here, we will have minimum potential, maximum kinetic, minimum potential, minimum kinetic here, we will have maximum potential. Position, this is when we have 0 potential energy because there is no height. So this represents this point. At maximum altitude, we will have maximum potential. Equilibrium will show us, give us a what? Minimum potential. Maximum displacement, maximum potential, and this is back to minimum potential. And the graph for the potential energy would look something like this. So you can see that if you join now both of these graphs together, total energy ET. And you can see that the total energy is a what? It's a straight line. Okay? Now, last thing that I need to highlight just because for your exam, that whenever you're given energy versus displacement graph, and they ask you to find what is the displacement for one full cycle, you should not consider this as full cycle, because this is half of a cycle. This is just the pendulum going from equilibrium to maximum back to equilibrium. And as we said here, one full oscillation should be starting from equilibrium to maximum, back to equilibrium, maximum negative, and back to equilibrium. So you should pay attention to what your x-axis said in order to be able to spot how long is one full oscillation. Okay, now we know that AK, kinetic energy, is equals to half m velocity squared. And this is from topic 2, of course, okay? What we took right now is that the maximum, it's here. The maximum velocity is equals to what? This is the maximum velocity, V0, is equals to x0 omega. So if I would like to find the maximum kinetic energy, I can replace half m v by omega x0 squared, okay? And this shows you the maximum kinetic, which is equals to the maximum energy that the pendulum, the system, will have. Now, all of these equations are found in the data booklet. Okay? These are the equations in the data booklet. Omega is 2 pi over t. This represents A max is minus omega squared x. X is x0 sine omega t. V is omega x0 cosine omega t. And A is not given, but anyway, you don't need it. This is for the maximum energy that the system will have. Mind you that this is what? This is, it's maximum V to the power of 2. Now, as for this one represents the velocity of the system at any point. Okay, so for example, if we have this variation, okay, the maximum point is V0, correct? The maximum velocity, which is equals to this, according to what we did before. And so say I want to know the velocity of the system at, let's say, this point over here, okay? So it's a random point on the graph, on the wave. And so to find the velocity at this point, you do omega x0 squared minus x squared, x of this point specifically, okay? Now, to show you that we can go from this relationship to this one, when x is x0, you will see that V is equals to omega square root of x0 squared, which is omega x0. And we go back to what? The maximum velocity of the system.